Research without a well-defined study design is like a spaceship lost in space. The study design is the compass guiding your research journey. It dictates the how, the what, and the why of your data collection and analysis. A carefully chosen study design aligns with your research question. Consider a researcher aiming to understand the prevalence of a rare star system. A descriptive study surveying a large expanse of the cosmos would be ideal. Conversely, investigating the impact of a black hole on nearby planets requires a different approach. An analytical study design, perhaps a case control study, would be more appropriate. By comparing planets affected by the black hole's gravitational pull to those outside its influence, researchers can draw meaningful conclusions. The choice of study design hinges on the nature of your research question. Are you exploring the characteristics of a phenomenon, or are you investigating cause and effect relationships? Defining your objective clearly is paramount. A well-defined research question guides the selection of the most suitable study design, ensuring that your research voyage is fruitful. In research, two primary approaches guide our quest for knowledge: observational and interventional studies. Picture observational studies as astronomical observations. Researchers meticulously observe and record celestial events without directly manipulating them. These studies provide valuable insights into naturally occurring phenomena, unveiling patterns and trends in the universe of data. Interventional studies, on the other hand, introduce a deliberate change into the equation. Imagine scientists conducting an experiment to understand the effects of a specific cosmic radiation on a group of asteroids. They manipulate the independent variable, the radiation exposure, and observe the subsequent effects on the asteroids. This approach allows researchers to explore cause and effect relationships, unraveling the intricate mechanisms that govern our universe. Choosing between an observational and interventional approach depends on the nature of the research question. If the goal is to understand the natural history of a disease or phenomenon, an observational study is often the preferred approach. For instance, studying the long-term effects of a supernova on a distant galaxy would necessitate an observational design. In observational studies, descriptive studies serve as the cosmic cartographers, mapping out the characteristics of a specific population or phenomenon. These studies don't delve into cause and effect relationships, but rather provide a snapshot of what exists. Think of them as celestial surveys, meticulously documenting the distribution of stars in a particular galaxy or the prevalence of black holes in our universe. One common type of descriptive study is the cross-sectional study. This design captures data at a single point in time, providing a snapshot of the variables of interest. Imagine a study examining the prevalence of a specific type of galaxy in a distant cluster. Researchers would analyze data from a single observation, categorizing and counting the different types of galaxies present in that cluster at that specific moment. Descriptive studies are invaluable for generating hypotheses and providing a foundation for further research. They offer a glimpse into the intricacies of our universe, highlighting areas where more in-depth exploration is warranted. While descriptive studies paint a broad picture, analytical studies delve deeper, seeking to unravel the mysteries behind observed patterns. These studies, still within the realm of observational research, introduce comparisons, allowing researchers to explore potential associations and answer more complex questions. Imagine investigating the factors influencing the lifespan of stars. An analytical study might compare stars of different masses, compositions, and environments, seeking to identify factors associated with longer stellar lives. One common type of analytical study is the cohort study. This design follows a group of individuals with a shared characteristic over time, observing the development of outcomes of interest. For instance, researchers might follow a cohort of stars born from the same nebula, tracking their evolution over millions of years. By comparing those that go supernova to those that live longer, they can glean insights into the factors influencing stellar longevity. Analytical studies are essential for understanding the why behind the what. They provide a deeper understanding of the relationships between variables, offering clues about potential causes and effects. Randomized controlled trials, or RCTs, stand as the gold standard of research. These studies, falling under the umbrella of interventional designs, are meticulously designed to minimize bias and establish causal relationships. Imagine conducting an experiment to test the effectiveness of a new fuel source for interstellar travel. An RCT would randomly assign spacecraft to receive either the new fuel or a traditional fuel, carefully controlling for other variables that might influence travel time. The power of RCTs lies in their ability to minimize confounding factors. Randomization ensures that the groups being compared are as similar as possible at the outset, reducing the likelihood that observed differences are due to factors other than the intervention being studied. This rigorous approach allows researchers to confidently attribute any observed effects to the intervention, providing strong evidence for causal relationships. Consider a study investigating the impact of a new training program on astronaut performance. Researchers would randomly assign astronauts to either undergo the new training or continue with the standard protocol. By comparing performance metrics between the two groups, they can determine whether the new training program leads to significant improvements. Quasi-experimental designs offer a valuable alternative for exploring causal relationships when random assignment is not feasible. Imagine studying the impact of a new space exploration initiative on a nation's technological advancement. It's impossible to randomly assign entire nations to receive or not receive the initiative. Quasi-experimental designs share similarities with RCTs, involving the manipulation of an independent variable and the observation of its effects on a dependent variable. However, they differ in that they lack the element of random assignment. Instead, researchers utilize various techniques to control for confounding variables and strengthen the internal validity of their findings. One common